Hey, we're being recorded. All right, so since I just spent like 5 minutes saying this, let's say it again for all those people who couldn't make it today. Doing a quick reminder of how we do the overall delta H's of a reaction. So I put up here, I think this is fructose, if I'm not mistaken. We got some oxygen, making CO2 and water. I went ahead and gave you the delta H naught of formations for each of these, and I'm going to ask you what the delta H naught of the reaction is. And this just to remind you of the cool shortcut that we proved, much to Issa's chagrin a couple days ago. She's like, why did you do all this? Because sometimes you need the long way to know the short way. So I'm just going to remind us of the short way because we're going to use it again here in just a moment. So what we're going to do is we're going to take, the products, which is going to be 12 times the negative 393.5 and the 11 times the negative 241.8. And we're going to subtract the 1, if you will, times the negative 2220 and the 12 times 0 for the water or the oxygen. And if you do that, you get the delta H naught of the reaction. So the energy we think that we should get out at the end of all this is negative 5161.8 kilojoules per mole. So if you were to go and say like, hey, I just want to burn all this sugar off, what are we going to, how much energy are we thinking is going to come out? Well, it's going to lose 5,000 kilojoules, which means we'll be able to gain it. So just sort of a recap of how that's all supposed to be calculated. So I don't think there's anything spectacular about that. I think that's pretty straightforward. I don't think anyone's got any problems with that. So let's go ahead and start talking about the delta G and S. Now that we've talked about the enthalpy, the internal energy, the inherent energy of any molecule, let's talk about delta G and S. Because those guys are going to come in here. Going to come into play. So delta G. This is the Gibbs free energy. Sometimes just free energy. Some people leave off Gibbs. Sometimes they'll just say free energy. And this is the energy available to do work. And then there's S. And this is a measure of the disorder of a system. Now, by disorder, usually, I mean, it's something that people say, but really what it is just how many ways can the system go? So if you think about it, if you were a water molecule sitting in the middle of a bunch of other water molecules, you could move essentially in any direction you wanted. If, however, you're a water molecule stuck against the side of the glass, you've cut off half of your places that you can actually move. You've become more ordered. So entropy is a measure of the degrees of freedom for those who are in math. You can think about it in terms of degrees of freedom. So the more you have, the more your entropy has just increased. Now, I also want to note something here. You can have we can have delta H not a formation, delta G not of formation, and S naught no F. Now, this is because there's no such thing as forming entropy from the elements. The elements already are entropically what they are. There is no formation. It all starts at 0 and goes up from there, kind of like Kelvin. So there's no formation here. It's just going to be delta H naught a formation, delta G naught a formation, or just S naught. So everything, the delta G's and delta H's is everything compared to the elements which have 0 energy to be formed. So actually, I don't need to put words. So delta H naught a formation and delta G naught a formation is because we are comparing the current energy to what it was if we formed it from its elements. S naught has no F because entropy is not formed from elements. Rather, it is just a measure of the order of the system. Whether it's an element or not, doesn't matter. It's saying, do I have places to move, places to go, things to do, or not? Entropy has an absoluteness. Think Kelvin. When we think of temperature, Kelvin, starting from 0 and going up, coming from a place where all movement stops, except the electrons around the nucleus. The quote 0-point energy. We usually don't have a problem with thinking about that in terms of temperature. I want to translate that to entropy because entropy actually is defined by temperature. And so you can envision that the more temperature you have, the hotter you make it, the more they can move, the more places they can go. So check it out. Entropy has an absoluteness. Entropy is 0 at 0 Kelvin. No disorder. Everything's frozen. Entropy is dependent on temperature. Man, my handwriting is horrible today. I apologize for that. Everything is everyone here? Dallas, can you just say something so I feel like I'm talking to some people?
Something.
Thank you. How long ago did this start? I don't know, like 7 minutes.
Do you mind scrolling up a little bit so I can see the first part of the
Hey,
note?
there are people here. What part do you want to see, Issa?
Just stop right there. I'll take a picture and then you can scroll back down.
That's fine. Keep writing.
Thank you.
So,
I'm good.
You're good?
Yeah,
I
thank
was just
you.
gonna blather anyway. So so when we talk about delta H is the energy of the bonds, delta G is the energy to do work. Entropy is different from these two. And it's different because it's not dependent upon elemental states or any of that. It's just dependent on the temperature. When you actually have no temperature, everything's locked down, you have perfect order. So there's no entropy. As soon as you start heating things up, stuff can move. When it moves, you've now created a place for things to go. When they can go, they have degrees of freedom. When they have more degrees of freedom, they are more entropic or have a higher entropy. Mother Nature actually loves to have things go to disorder. Just settle it down where it will. Doesn't necessarily like to order it. In order to put things in their place, you have to pick them up and put them there. That takes energy, and Mother Nature doesn't like to take energy. What's going on in the chat there? 917. Hey, I was right. Okay, so when we look at entropy, the higher the temp, the higher the disorder. The higher the temperature, the more disorder. You can think about this even insofar as just what's happening here in spring. The more, there are more notes than just that? No, this is, look, this is all there is here. We started there. Okay. Are you with me, Tanaris?
Yeah,
Okay. Did you already get that?
I just took a picture of it.
Okay. And then we did this. Do you want to take a picture of that?
Yeah, I took a picture.
Okay. And then we're basically here.
Okay.
All right. So if you think about entropy, even insofar as our current daily lives right now, just a few weeks ago it was cold. We didn't mind being stuck inside because it was cold outside. We didn't want to do anything, but now it's warmed up, and the only thing we want to do is actually get out and go and enjoy the warm air. We want to move. We want to go somewhere. We want to do something. Entropy is the same thing. Entropy is absolute. When we look at a difference between two conditions, it's just a delta S. So when we compare entropies, we are comparing against each other. What I mean by that is they're all coming from the place of zero, but not necessarily in elemental states. So the delta S period of a reaction is equal to the S of the products minus the S of the reactants. Notice that there's not a delta H equals a delta H of the products and a delta H of the reactants. It's just an S of the products and the S of the reactants because they're all coming from exactly the same spot. Whereas every compound in a reaction is coming from different elemental states, different elements, and the energies associated with them will be different. Entropy is an absolute. They all come from zero and go up from there. So we just talked about the entropy, not the change in the entropy of the products, but where are the products now? Where are the reactants now? So what is that difference overall? It's a subtle difference, but it's a difference. Is that you, Dallas?
Yes, it is. You said that entropy is temperature dependent and that higher temperatures go along with higher entropy. Is that correct?
Yes, in general, yes.
So then wouldn't the constant cooling of the universe go against the second law of thermodynamics?
Well, you're getting into some freaky shit right there. I'll tell you that right now. Is because if it's constantly cooling, Dallas, where is it losing its heat?
Oh, it's the heat is just being distributed across a larger volume.
Because it's expanding, yes?
Yeah.
Into what? Yeah, until you can answer me that, mind blown, STFU. I mean, seriously, I mean that in all affection, because at this point we're starting to get into religion, because it blows my mind that the universe is ever expanding, and yes, it is cooling down. If you want to get down to it, Dallas, that is exactly. If you ever here, I'll just stop. Stop sharing for a second, and pull out the video here, and pull it up. Let's take a look. You seen one of these things, Dallas? Compressed air, right? I go like this, right? Compressed air. It's cold. It's cold because I have all of these gas molecules compressed inside of this can, and I'm suddenly just letting them go out the tip and do nothing. All right, they're not doing any work. They're not doing anything with their energy except for just expanding. What we call an adiabatic expansion of a gas. You just let a gas do its thing, expand like it wants to, and do nothing with it. When you do that, you have now essentially increased the entropy of the system from ordered to not ordered, and the energy has to go somewhere. And what it does is it makes the can cold. So, yeah, the universe is cooling down. Why? Because it's expanding and doing nothing but just expanding. Okay, I'm cool with that. Then, of course, you want to say expanding into what? Yeah, now we're in the high country. So, yeah, some of this goes beyond the scope of this class, or in many respects beyond the scope of science, as far as I'm concerned. Now, what is entropy and what is delta G? Let me give you my best shot at what entropy is. And entropy example. Oh, I gotta get my participants back here. There we go. Oh, I get to use my colors too. All right. Popcorn. I'm going to have some red kernels of popcorn in one nice perfect layer. Then on top of that, I'm going to put some green popcorn kernels right on top of it in one perfect layer. And then I'm going to have some blue popcorn kernels in one perfect layer on top of it. Can we agree that we are pretty ordered here? Deafening silence says yes. Yeah. So this is very ordered. What I'm going to do next is I'm going to put a little fire on it. What's going to happen to this popcorn? I guess I should note that this is all popcorn. What's going to happen when I do this? Does anyone cook this stuff anymore? Alexia, you're here.
So the popcorn's going to heat up and then pop. and then as it pops, it'll be sort of thrown up, mixing the whole system up.
That is correct. So, oh, that was a bad line. So if we envision this in the aftermath, you're going to have all this stuff mixing around. It's not going to all pop up at once and just keep their nice little order. It's going to go everywhere. Okay. So when it does this, it becomes disordered. So if we think about this example, and I like this example, the delta H in this system, this is from popping. We took all that stored energy that was inside that kernel, all that little watery shell that was inside that husk of the corn kernels. We gave it some heat and we said, boom. And we have a change in the internal energy of that kernel, turning it into a piece of popcorn. The delta S is mixing the popcorn. The delta G is this energy that we got from popping it minus the energy that we lost to mixing, the entropy from that. And you'll notice, again, I put the temperature in there. Now, in this case, in some respects, it's hard to think about this because you're popping popcorn, so it's just at a temperature. But if we could pop popcorn at different temperatures, you would actually see a different amount of mixing. If you could pop it like super fast or super slow, you might see a difference in that mixing. Now, some people might ask, okay, but I don't understand. What do you mean this delta G, this energy we get from the mixing? So this is the energy overall that we can do to do work. For the few of us that have ever actually popped popcorn by hand instead of using a microwave, I had this wonderful, wonderful pan growing up in my youth. I still wish I would have somehow, if there were one piece of cookware that I could still wish to have, it would be this pot. This pot, I don't know what it was made out of, but it had this beautiful lid that had a little popper valve on the top of it. And I would use it to pop popcorn. And I put all my butter in there and just cover it on the bottom. And I get these, I gotta show you guys this. This is, you gotta see the enthusiasm here. So we have this pot and I just put all this butter. It's like super thick layer of butter on the bottom. And then I just sprinkle all my kernels until they make a perfect one layer across the bottom. And then I do it again to make a double thick layer. And this pot was beautiful. I'd sit there and I'd shake it. And on the top, there's this little popper valve. I don't even know why, but it had a little popper valve that would let off steam. And I could see every time that a kernel popped, this little popper valve would pop up and down. And as I got more and more going, it would go faster and faster. So it was like this steady stream coming out. And because I made the 2 layers, it would like make the lid like just barely crest over the top, almost brimming with popcorn. And that's how I knew I made a great batch of popcorn. Delta H was taking the kernels to the popcorn. S was popping them all around and making them mix up. The G would have been if I could have put some sort of little mechanical device on the little popper valve. Pop, 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 pop. Every time it pop, 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 popped, I could have actually taken all that energy and moved a valve and done some work with it. Now, I know that it's kind of weird to think about that, but that's essentially what we do when we blow up anything to move a piston to do some work. I'm just doing it on a very minuscule way with a tiny little popcorn valve. Now, I'm going to put a couple of important equations here, and then we'll start working with them. Man, is everyone else as tired as me? Because like, even Dallas isn't talking very much.
Yeah, nope, exhausted.
Can somebody else confirm that besides Boudica, because she's always tired?
Very tired.
Okay. For a minute, I was thinking like, man, am I really that dull today? Because it's okay if I am, but I'll take it. I'm tired. Important equations. Delta G is equal to delta H minus T delta S. The higher that temperature, the more the entropy is going to contribute or not contribute to what we want to do. And delta G naught is equal, or sorry, delta G is equal to delta G naught plus RT natural log of Q. These are two equations that we're going to be using a lot. Now, you notice that we have a delta G, and now we have a delta G naught. There's a Gibbs free energy that you get overall, and then there's a Gibbs free energy you get from looking at it forming from its elemental state. So the Q is interesting. So Q is going to be the products over the reactants. Now what this is, it's a measure of how far away from equilibrium we are. This is how far away from equilibrium we are. So what we're going to start seeing here is the delta G can be related directly to the energy before and after of those bonds. Also, do we do any entropy work there? It can also be related to what you would expect in general if you were just building this from its elements, and then comparing that to where you are if you aren't where you should be. Okay? Remember, we talked about equilibrium is death. We're going to start shoving things away from equilibrium and see how much work we can do. And now we have it right there with that RT ln Q. Now, you recognize R, that's the gas constant. You recognize T, that's temperature. Here we have that temperature effect showing itself over and over. So just to remind ourselves a little bit more, let's break it down a little bit here. We have a delta G equals delta H minus T delta S. This is the free energy. All right, energy for work. We have the delta H. This is the energy difference between bonds. Products minus reactants. And then we have this guy, and this is just energy lost. Some people call it Mother Nature's tax. We can't get anything useful out of entropy for the most part. So how does this all work? We have all these equations. Let's start putting them into practice here. So put it into practice. See, I have 1 molar HAC plus 0.02 molar HCl plus 0.5 molar NaAC. Dump them in a pot. Yeah?
Quick question. So our two delta G equations, both of them are dependent on temperature,
Mm-hmm.
but one of them is positively correlated with it, and the other seems to be negatively correlated with it.
Oh, I love math. Yes, you're right. It looks like one is positive and one is negative, but you'll find that that other one that you think is positive, the bottom one with the RT land Q,
Yeah.
is actually not positively correlated. Because when you start putting in the concentration of products over concentration of reactants, you will start,
Ln's going to be negative.
yeah.
All right.
So, yeah, it's funny. It's like, wait, you can't just rely on what you see because things get a little weird. Okay, so say I have all these things, I dump in a beaker and let them go at it. You know, at 25 degrees, just because. All right, normally we would say HAC goes back and forth to make H plus, AC minus, and we have our 1 molar, our 0.02, and our 0.5. Now, normally, we used to solve this to actually figure out an equilibrium constant. We used to use this to get KEQ. Now, we can figure out how much energy we get while these guys go to equilibrium. So now we're going to look at this problem in just a slightly different way. Instead of getting a KEQ, which we can do with our eyes closed now, we're going to actually look at this and say, look, if we put these things in there, we know they're going to go to an equilibrium. So if they are, is there any energy that is going to be associated with them moving to that equilibrium? So we look at Q, which is the products over the reactants. In this case, our product are the H's and the AC minuses. So we would have 0.02, we'd have 0.5, and we'd have the 1 for the reactants. If we look at this, this is where we're starting from, and we're going to go to equilibrium, which is where nothing is going to happen. So this number, as it were, is how far away from equilibrium we are. So what we're going to do is we're going to take a look at this. We're going to look at the fact of work is what we can get out in the delta G. We're going to compare this work to the work that would be done at equilibrium. So to compare this to equilibrium conditions, consider the following. At equilibrium, delta G is equal to 0, right? There is no driving force. Everyone is in its place. Now, what that means then, if the delta G is 0, this also means that this quotient, this ratio of products to reactants is actually what it would be at equilibrium. Because if they're not going to have a driving force to go left or right, then this quotient here of products over reactions must be what we would see at equilibrium. So, if that's the case, and delta G is equal to delta G naught plus RT ln Q, and we go to equilibrium, then delta G naught becomes 0, right? We're going to go to equilibrium. That becomes 0. Delta G naught stays the same, but now this is RT ln KEQ. Which means, if we solve this, the delta G naught is equal to negative RT natural log of the equilibrium. So when we start looking at the delta G's, and we're trying to find it as it's going to equilibrium, okay? And that is going all the way back up to that delta G equals delta G naught plus RT ln Q. If we put delta G naught equals the negative RT ln KEQ, then really what we are looking at as, and let me just sort of just put that in there. So this means delta G is equal to negative RT ln KEQ plus RT ln Q, right? That's putting those things back in. We can factor all this out, and that means that it's RT natural log of Q over KEQ. So the delta G is comparing where we are to where we're going. So this means delta G is comparing where we are to where we're going. And to just sort of put that back into plain speak again, delta G is delta G naught plus RT ln Q. we could say that this here is the usable energy. I think usable doesn't have an E. No, I think it has it. This is the energy at equilibrium. And this is how far away we are. Now, just because we're at equilibrium doesn't mean that there's not some sort of energy associated with that, because there's always the energy of the bonds of everything that already is at equilibrium and the measure of the disorder of the system going right back up to this guy right here. There's no difference in talking about this as an overall reaction at any given temperature and any given conditions, and saying we're going to do it at standard conditions, putting knots there. You will still have some internal energy, the enthalpic energy. You will always have some entropic energy, even at equilibrium. You just may not be able to do anything with it. Okay. So, back to our problem. I'm going to look up delta G naught for acetic acid. It's in the book. You can find it. People have done this. They've calculated it. So delta G naught of acetic acid is equal to negative 389.9 kilojoules per mole. That's what it is, standard conditions. So what is it now? Delta G is delta G naught plus RT natural log of Q. So it's negative 389.9 kilojoules per mole plus R, which we now remember is this 8.314 joules per mole Kelvin. We said we're at 25, so we'll make that 298 Kelvin. And now we have a natural log of, I think that's 0.01. I calculated that right. I'll be right back for it. And of course, remember, I've got a kilojoules and a joules. So make this kg, kj if you want. If you do that, you'll end up with negative 401 kilojoules per mole. What that means, it is spontaneous. It will naturally go to its equilibrium state without you having to do anything. Give me just a second. Hunter, please stop recording. So as we look at this, we expect that to happen, and we know that because of equilibriums. If we go right back up here, where did my equation go? If we look right here at these guys, we expected this thing to reestablish an equilibrium. We've been working with acetic acid for 6 weeks now, and we know that its equilibrium constant is 10 to the minus 5. So those concentrations of H plus and AC minus are ridiculously too high for what it wants to do. So what it's going to do, it's going to do just like what we calculated for the last exam. We're going to have to shift everything over, let it re-trickle back, and find that we have almost nothing left of our stuff, because all those H pluses are going to be consumed by AC minuses to make acetic acid molecules. And that consumption is going to be spontaneous. It's going to just happen. And thermodynamics tells us this. Yes.
So does the delta G that we got for our answer, does that mean like how much energy it took to get to equilibrium?
Yes, or we'll give off, right?
Right. Okay.
And so the question is, now the philosophical question for Dallas is, so how do we get that energy? And in fact, we don't, unless you, well, there could be ways, but I don't know them. But supposing you could make some sort of engine that these things had to go through to do their equilibrium rebalancing, you could harness that energy. Now, physically, I don't know how you could do it in a situation like this, but I'm sure there are ways for other systems. As all you're doing is taking any reaction, shifting it out of equilibrium, and then letting it go back. This is rechargeable batteries, guys. You take and you pump a bunch of energy in overnight, you shove those ions back to their starting positions. The next morning, you light up your phone, and the phone says, I need energy, opens the floodgates for those ions to start flowing back across the channel, and you have your work going on because you're running it through a wire to power your device. Go ahead, Dallas.
I'm getting negative 387.4 kilojoules per mole.
Negative 387. So did somebody lie to me in a previous class?
Probably.
Did you guys do
Possible.
the same thing?
I'm getting 401, negative 401.
I got 401. Done. I have confirmation. Thanks, Chef. Hitting my back there. All right. Let's start looking at some more calculations along this line. Let's start looking at some systems here. We're going to get some cobalt 2 chloride. And it's going to break up to be cobalt 2 pluses and 2 chlorides. Now, what I want to do is I want to calculate delta G naught for this dissolving. To do that, I'm going to look up some stuff. So I'm going to get my ingredients. I'm going to get each of those delta H naughts. These are going to be in kilojoules per mole. And I'm going to get their S naughts, which are going to be in joules per mole Kelvin. The three ingredients I have for this system are the ones right up here. I have the cobalt 2 chloride. I have the cobalt ions floating around and the chloride ions floating around. As I go to the book, right, I'm gonna calculate. We need this stuff. We're gonna look it up. The delta H naught for cobalt 2 chloride is negative 325.5, and its entropy, sitting right there at 25, is 106.3. So even as a solid sitting around, it has a certain amount of entropy because it's got a temperature. Cobalt ions swimming around. H is a negative 67.36. The entropy is negative 155.2. The chloride is negative 167.4, and the entropy is actually positive 55.1. Now, given this information, we should be able to calculate the delta G overall. So if we remember, delta G naught is equal to delta H naught minus T delta S naught. All we have to do is figure out the delta H's and the delta S's. So this is why we spent last class period doing all the delta H's, products minus reactants. We're going to do the same thing for all of this. So keeping this in mind, we're going to go with the delta H naught. This is equal to the products minus the reactants. So our products are the cobalt at a negative 67.36 plus the chlorides, and hopefully you guys remember that since there's two of them, we're going to multiply that by 2. So negative 167.4. And we're going to subtract out the reactants here, which is the negative 325.5. And this whole thing happens to be in kilojoules per mole. So if we do that calculation, you should end up with negative 76.66 kilojoules per mole. This implies that this dissolving is exothermic. That is favorable. Now, before I go much further on that, I just want to point out that this kind of makes sense a little bit. As long as we can make sense of these things, we should. Does cobalt chloride want to dissolve? Dallas?
Yes,
Why?
because chlorine likes to dissolve.
That is correct. Now, it turns out that a lot of dissolving processes, whether you know this or not, they tend to be exothermic. That when you mix them up, they will release some heat. There are a few that are endothermic, but most of them are exothermic because the new if they want to dissolve, the new bonds they form or the new interactions they form with the solvent cage was of lower energy than being stuck together. All right, so we have a delta H naught. Let's get a delta S. So our delta S naught, this is the products again, minus the reactants. So we just put that in there. We got a negative 155.2. And again, we have 2 chlorines there. So it's 2 times the positive 55.1. And we take the reactants. And so minus 106.2 or 3. Can't read my writing. 3. Now, I want to point out that this is joules, not kilojoules, but joules per mole Kelvin. And that means negative 151.3 joules per mole Kelvin. That means it becomes more ordered. For whatever reason, that dissolving process, Mother Nature thinks that that's a better place for it to be. The question is, overall, what is our ability to try to get some work out of this dissolving process? So
Wait a minute.
I know, right? I know. Sometimes it blows your mind, doesn't it, Dallas?
No, you said that becomes more ordered and that's a better place for it to be according to nature.
Well,
Does it?
it's saying that if we're just looking at entropy, I didn't say that Mother Nature said it was a better place. It says that as far as the cobalt's concerned, it would much rather go to this. I should say not go to this place because it looks like it's becoming more ordered than where it was. It's a weird mind twist on this, and entropy does that to you. And so,
For it to be positive?
is it possible for it to be positive? Yes.
Why
In
would
fact-
it be positive though?
Well, if you think about the entropy, the products minus the reactants, if it is more disordered, which is a favorable thing, coming from a more ordered spot, then the entropy would be positive. Mother Nature loves that to do its thing, and it'll go. Now, this is where it gets kind of weird because you think, okay, a solid chunk now is dispersed through water. Technically, it has more places to go. That's more disordered. But according to the math right now, it's saying that doing this, Mother Nature, for whatever reason, thinks that it's more ordered than disordered. And I know that that's weird, but sometimes you just let it go. Because what happens is, and this gets weird, and I've talked to my colleagues about this aspect on more than one occasion where I'm like, wait a second, you're telling me that solid where it's all stuck together is less ordered than those ions floating around in water? And they're like, yep. At 25 degrees Celsius, that's what the numbers tell us. Now, I still go, but it's a solid and these things technically are floating around. They're like, yep. And we basically go round and round about the idea that what we considered ordered and what Mother Nature considers to be an ordered state don't always coincide in our brains. Mother Nature has her own idea of how she wants things to be, and it doesn't always coincide with what we want it to be. So sometimes the physical realm makes sense, and we go like, oh yeah, totally, I get that. And sometimes you go like, But what I want to point out is at the end of the day, even if entropy does a little mind warp on us, even if it's like, oh wait, at the end of the day, it's less about the entropy and more about what we're about to calculate, the total energy of the system. That one is always going to make sense to us. That one will always make sense to us, even if one of these guys doesn't quite make it. And you'll see what I mean in just a second. So if we do this delta G, the negative 76.66 kilojoules per mole, we're going to subtract out, since we're at 25 degrees because of the knot, 298 Kelvin times this 0.1513 kilojoules per mole Kelvin, right? Because we got to convert that joules to kilojoules. So joules to kilojoules, we're going to have to move that. At the end of the day, this is negative 31.6 kilojoules per mole. So when we do that, that means delta G naught is negative. So this is a spontaneous process. So did I spell process right? Hold on. So let me explain how, even though entropically it says, hey, you're trying to make me do something I don't want to do. The enthalpy says, don't worry, I'll give you enough energy to do that. If you just let me do it, you'll be happy. And so entropy goes, all right, hold on. I'll work with you. I'll let one of me break apart and you prove to me that the difference in the energies before and after you breaking apart and floating around will give me enough energy to do something I don't want to do. And it says, okay, I'll take that bet. And as soon as one of those breaks apart, the rest of them go like, oh, that was easy. And boom, overall, enthalpically and or even against the entropy, it says we will go. So it's actually a combination of the before and afters of both the enthalpy and the entropy. They don't always have to be in concert with each other. One could trump the other. Now, at a certain point, if you raise the temperature enough, you may end up finding out that you don't want to do this, right? Because you would increase the entropic effect. There are, believe it or not, there are some solids that are soluble at room temperature, but you heat them up and they precipitate out. Oh, I want to say that one more time because I'm waiting for Dallas to say, wait, what? There are solids out there that at room temperature, they will dissolve. If you heat them up, they will precipitate out.
Would that normally be weird?
Yes, because normally, if you think about it, Dallas, if you have sugar and you dump it into iced tea, does it dissolve?
I don't know.
Okay, think about.
No.
Thank you. It doesn't want to dissolve. You have to mix it and mix it and mix it until you finally get it to. Now, the truth of the matter is, it does want to dissolve. It's just going to go very, very slowly because it's cold. You take that same sugar and you dump it into hot tea and boom, it's gone. Why? You have increased the entropic effect of that dissolving process. Okay? Usually when you heat something up, it wants to dissolve. But there are plenty of solids out there that will actually go backward because of this entropic effect that you see right here. It doesn't make any sense. Physically, it doesn't make any sense because you're like, wait, if I heat it up, it should want to dissolve. But there are plenty of solids out there that as you get them hotter, they're like, no, peace out. And they precipitate out. Now, for those who've been with me for a long time, Chem 110, I want you to set the way back machine. Chem 110, we did the types of reactions, and we were looking for precipitates, evidences of chemical change. And one of those took some calcium nitrate and some sodium sulfate. And you went drip, 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 and many of you saw nothing happen. And you're like, nothing happened. And I'm like, yeah, it's just a physical process. It's just mixing. And then some of you, I may have gone around and I held it in my hand for just a couple of minutes and you saw that it got cloudy. And that was because the heat of my hand on that solution was just enough to make the calcium sulfate come out of solution just a little bit. I heated it up just a little bit. And in fact, the original description for this type of reaction actually tells students, if you don't see it precipitate, heat up the liquid. But as we all know, do we heat up liquids in test tubes?
No.
There you go. So I took that part out because the last thing I wanted to have was people heating these things up in test tubes incorrectly and blowing everything up. But when I'm in the right place at the right time, I've been able to go and just with the heat of my hand, make it come out of solution. So just because the individual portions don't necessarily make sense in the case of this entropy for this one, that's because the whole system might not make sense for our intuition. There are things that sort of go against the grain. But overall, when we started this problem, I said, hey, you've got cobalt chloride breaking apart. And Dallas goes, of course, because chloride wants to swim. That's great. And we looked at the enthalpic contribution. We're like, yeah, it totally wants to. Then we look at entropy like, but overall, it does exactly what we think it should do, and that is dissolve. Because the delta G says, yeah, you want to do that. In fact, what I want to do is I want to find out just how much it wants to do it.
Yeah, it's a quick question. So if it's becoming more ordered, but it does it anyway on its own,
Mm-hmm.
wouldn't that imply that it's again breaking the second law of thermodynamics?
No, because it's the overall, Dallas. You're looking at one portion. You're looking at one portion saying, oh, well, no, it's breaking thermo. No, because it's a combination. Breaking thermo would say, if that delta G said, well, actually, nothing here is broken. Even if this delta G were positive, all I would say is, yeah, that cobalt chloride, not going to happen. Now, again, if you want to make this thing not happen, Dallas, if you want to say, look, give me a situation where it won't, then change that. Make it 29,000 Kelvin. Make that entropic effect so great that delta G becomes positive, and boom. But remember, but what we're asking here is, will it happen at this 25 degrees, at this delta G naught, at the room temperature we're asking it? Would cobalt chloride dissolve? Yes. Even if there is a portion that says, I don't want to, the other portion dominated and said, forget it, we're doing it anyway.
If I'm hearing correctly, you're saying that one portion of it becomes more ordered, but something else is becoming more disordered.
No. This says overall, for whatever reason, as it dissolves, it feels like it's becoming more ordered at 25. What I'm saying is, even though this one appears to be like, oh, but Mother Nature wants it to be more disordered. Why is it becoming more ordered? Because this delta H is pumping all that energy into it to override the entropic effect. You keep thinking about these in one piece at a time, Dallas. You need to think about it in the overall picture. It's the difference of bond energies and the difference of ordering and disordering as to whether or not overall it wants to go. Do you see? Maybe not.
Nope.
Okay, I know, because it's kind of weird. I mean, if you think about it, why is it that up here in the entropy, the cobalt is more ordered, but the cobalt chloride and the chlorine are more disordered? I don't know. I didn't do the measurements. That's outside of my pay grade. Other people who do these experiments said, I don't care. These are the numbers. But what I do know, Dallas, is at the end of the day, the difference between the energy of the bonds and whether or not it does or does not want to become more or less disordered, when I get down to the end of the day, those two competitive or concert effects tell me we are going to go ahead and dissolve, just like we know from our solubility rules. Chloride wants to go swimming, it's going to go swimming. You can't look at one piece anymore, Dallas. You have to look at the whole picture, because they will compete or help each other, but you don't know until you get to the end equation. So yes, this guy is favorable. This guy is unfavorable. At the end of the day, it is spontaneous. It's favorable, even if there's a competitive effect. So now, what is the KEQ? What's the equilibrium of this? Well, remember, we just above proved delta G naught is equal to negative RT natural log of the equilibrium constant. So we can plug that in. So we get a negative 8.314 joules per mole Kelvin. We're at that 298 Kelvin. and we got a natural log of the KEQ, which is what we're looking for. And that's equal to our delta G naught, which is negative 31600 joules per mole. Now again, I went from kilojoules to joules just to make sure those all match up. So if I solve for the KEQ is equal to E of the negative 31600 joules per mole over the 8.314 joules per mole Kelvin and the 298 Kelvin. And Dallas, I bet at the end of the day, you're going to tell me that that's 346,079. Or you're going to argue with me and say, no, I got something different.
I got 33698.
33698. Cool. I don't feel like arguing. All I know is this. Stupid soluble. So I'm going to go ahead and do that anyway. 31600 divided by 8.314 divided by 298. And I'm going to hit E to the negative answer. Oops. No, I don't want to do that. I want to do 31600 divided by 8.314 times 298. And I'm going to E that whole thing. Yeah, you're wrong. You rounded. So the interesting thing about what we just did there is, and I just want to sort of recap all this for us here. We started out talking about, whoa, we're way up here. The Gibbs free energy being a combination of the enthalpic and entropic conditions with the delta G equals delta H minus T delta S. I also gave you an equation to use, the delta G equals delta G naught plus RT ln Q. And what that is saying, look, we're going to look at the Gibbs free energy by comparing a reaction where it's at equilibrium, the delta G naught, to if we're outside of equilibrium with the RT ln Q. We then just took a look at a system that we would normally look at in an equilibrium case, trying to figure out what is the KEQ of this thing, and we have to shift and trickle and stuff. And I said, let's look at it from now, not that aspect, but the energy aspect. If I dump all these things into a beaker, clearly we're out of equilibrium. I just want to know how much energy is coming out of that. So along the way, I went ahead and reminded us that delta G naught equaling 0 says there's no driving force. We are at equilibrium. And if that's the case, then this delta G equals delta G naught plus RT ln Q is really just nothing equals that Gibbs free energy at 25 and its equilibrium conditions. So we now have a way of relating the delta G naught to an equilibrium situation. We went ahead and said, okay, well, if we dump all those in, what are we looking at? I went ahead and looked up the delta G naught of acetic acid, said, okay, what's its inherent free energy there? And you're like, oh, well, it's got something. Now that we've shoved it out of equilibrium, what more can we get? And even though it went from 389 to 401, not very much energy difference, it was enough, and it was spontaneous, and we could do something with it. And then I said, okay, well, let's consider just throwing a chunk of cobalt chloride into water. Will it dissolve? And Dallas goes, of course it will, because it's got the chloride and the solubility rules. Don't be silly. And I said, okay, well, what kind of energies are we looking at? And then what is the end game? Relating it all the way back to something that we know, and that is the equilibrium constant, the KEQ. And so I said, look, we're going to get delta G naught. Plenty of people spent a lot of their years figuring out that the delta H's and the S's for each of these systems, whether it's the cobalt chloride or the cobalt 2 plus or the chlorides. And even though some of them may not make sense, Dallas, that's what the measurements tell you. At the end of the day, we're looking for, is it going to be spontaneous or not? And I'm not just talking about the H's, I'm not just talking about the S's, I mean the overall system. Well, we looked at it, we said, the H's say it's exothermic. We would love to do this. The entropy, for whatever reason, goes, I feel like I'm becoming more ordered. I don't like that. But at the end of the day, the combination of the energy of the enthalpic bonds versus the ordered or disorderedness of the system says, yeah, we are going to do that. Following exactly Dallas's intuition of, yeah, chlorides are soluble. Of course it's going to go. What you didn't know on the back end, Dallas, is there was a competitive effect. We only knew the end result of the black box, not all the intricacies inside. Once we knew the delta G naught, I said, well, let's relate it back to something that we all know and love, and that is the equilibrium constant. And we said, okay, if we have the delta G naught equals negative RT ln KEQ, we can solve for that. And when we do, we find out that if we were to look up the equilibrium constant of throwing cobalt chloride into water, the KEQ would just say large. It probably wouldn't even be, it wouldn't even be on the register to say, okay, it's 300,000. It would just go like, yeah, it is going to dissolve. I get excited about this point because now we're starting to see how a lot of the concepts we've been looking at are going to start tying together. We're going to be able to start looking at a problem from a lot of different angles. Let me see if there's something. Go ahead.
So I'm looking at these equations, right? And a lot of them feature the, ln of products over reactants.
Yeah.
And it occurs to me that if we were to do something where we started out with no reactants or,
You still there? Uh-oh, what happened, Dallas? Or is it me? Hello?
It's not you.
Oh, Dallas, come back. Dallas. Uh-oh, we lost him. I can clean up my natural log while he hopefully comes back. Oops, let's get that back in purple. Well, I don't know what happened to you, Dallas, but we can't hear you. So I'm going to assume that you are busy contemplating the wonders of the universe in your brain, and you'll figure it out. Okay. Let's take a look here at just sort of proving how they get all their numbers here. Say a little like a slight proof here. Because sometimes you can look up delta H's and S's, and sometimes you can actually go straight to the delta G's. So I just want to point something out here. I happen to look at C2H6 plus four chlorines goes to make a couple of carbon tetrachlorides and 3 hydrogens. Notice in each one of these ones that I've done, at least one of them is on the 1 molar basis so that we can actually get the knot values. And what I want us to look at is the delta G naughts in kilojoules per mole, the delta H naughts in kilojoules per mole, and the S naughts in joules per mole Kelvin. I'm going to go to the books and I'm going to find them out. So for the ethane here, it's negative 32.89 for the delta G. Can you guys postulate what you think that chlorine is going to be for a delta G naught? It won't cost you nothing to guess.
Is it 0?
Hey, it's 0. And why would it be 0?
It's an element.
There you go. So just like with the delta H, the delta G's, nothing. At that situation, they don't want to have anything. Now, that doesn't mean that there isn't some entropy in these things, though, which is kind of a nice little twist again. The delta H is negative 84.08 for ethane, and the entropy is positive 229.5. Well, it turns out even if there's no delta G, no delta G naught energy, it will have entropic energy. It's at a temperature. So that's 222.9. It's still zooming around the universe with some temperature energy, so it has entropy. Going down for the carbon tetrachloride, it's negative 60.63, negative 103.0, and 308.7. And of course, hydrogen is zooming around with 130.6. Now, if I were to do the delta G's straight away, do delta G naught of this reaction straight away. Of course, we know that delta G naught, just like everything else, is equal to the delta G naught of the products minus the delta G naught of the reactants. And we have to remember that we have the stoichiometry involved here. So I'm going to have 2 times the negative 60.63. And I'm going to go ahead and remind us there was another thing in there. So we got 0 minus the negative 32.89 plus nothing again. And remember, this is all in kilojoules per mole. If you do this, you should get something like negative 88.37 kilojoules per mole, which means it's spontaneous. Once you get it going, it'll go. But I want to compare it to if you didn't have delta G straight away, but you only had access to the H's and S's. They don't have all the numbers for all these things. Sometimes they don't have them because no one bothered to do it. So I want to point out that you can either do it with delta G's if you have them, but what if you have only the H's and the S's? Does it compare to the delta H naught and the S naught data? So my delta H naught is equal to 2 times the negative 103.0 plus the other one, which is nothing, minus the negative 84.08 plus its elemental of nothing. And we find out that it's negative 121.92 kilojoules per mole, because we got to remind ourselves that was kilojoules per mole, which means that it is exothermic. And as far as this portion is concerned, that's a favorable interaction. Let's look at the delta S. So that's the products and the reactants again. 2 times 308.7 plus, now we got some numbers, 3 times 130.6 minus 229.5 plus 4 times 222.9. And remember, this is in joules per mole Kelvin. If you do this, you get negative 111.9 joules per mole Kelvin. And while the former one might be harder for you to think about, Dallas, this one might be a little easier to explain, because what you have is ethane plus the chlorine making some carbon tetrachloride in the hydrogen. And entropically, when it's talking about being more ordered or more disordered, Mother Nature saying making those products from those reactants actually puts them in a more ordered place. So while the dissolving may seem a little weird, hopefully you're okay saying like, okay, so you got this ethane, you got the chlorines, okay, I'm gonna basically rearrange them, and then in that rearranging, I'm actually going to order them a little more than they were before.
And you're saying that this thing happens?
Watch the magic, right? So this is more ordered, and that means it's not favored. But, so this is for Dallas, a big but, right? Again, do not look at the pieces unless I ask you a question about the pieces. Look at the overall. It's not very favorable, but its units are joules, not kilojoules. So if we do this, delta G equals delta H naught minus T delta S naught, we have negative 121.92 kilojoules per mole minus, since it's the naught, we have 298 Kelvin times 0.1119 kilojoules per mole Kelvin. So I just want to point out, Dallas, they're different units. And yeah, it's not very favored, but by what? 1,000 times less than that enthalpic difference of breaking and reforming those bonds. And if you do that math, I get negative 88.6 kilojoules per mole.
Yeah.
So it matches within reason, right? We have experimental errors on some of these values. Let me just double check something before I wreck something here. Can I do that in the allotted time? I don't think I can. All right, we're gonna save that for next time. I got my cool full circle example will be on Tuesday, and it will be glorious. I promise you. You probably won't care, but I think it's one of the more glorious things we do. All right. Aside from the man, I just don't get it question yet. Are there any questions?
Yeah, where can we find the recorded lectures?
What do you mean? You mean the one we did last time that I haven't posted up because I was trying to splice it together because we had an issue and I haven't figured out how to do that, so I haven't posted it?
Right.
Or do you mean all of them?
I guess all of them.
They're on the YouTube thing. They're on the modules in the Canvas. You should be able to go to Canvas, and aside from the one a couple days ago, I think I'm just going to give up and post 2 videos for you guys to watch. But you should be able to go into the modules, and all the YouTube videos are there.
All right.
Any other questions? What's going on? Necromancy. Wait, what, how do all I see is the word necromancy? What did I miss here? How can
Whatever
you
you missed on that one,
stupid
everyone missed.
soluble and just soluble. Stupid soluble means, I mean, we were at 300,000. I mean, the driving force to dissolve that cobalt chloride is just huge. I mean, they're soluble, and then there's just like, it's off the scale soluble. And so it's not, usually if it gets above 1,000, they'll just say large at times. Sometimes they'll go through and do the numbers, and sometimes they'll just be like, yeah, it just is. So just like when we were doing equilibriums and we said, okay, acetic acid, it's soluble. Okay, like 1% of it. And then we go to something like aluminum hydroxide, it's 10 to the negative 33, or that sulfide was 10 to the negative 52 or something like that. Yeah, that's stupid insoluble. So I guess soluble versus stupid soluble, it's a gray area, but I would say once you get above 1,000, it's moot. Be sure to like and subscribe and hit the bell to get notifications. What's that mean?
That's funny.
It's something that like every YouTuber ends all of their videos with.
Oh, is that what it? If you found this useful, like it in something. Okay. Why did you say necromancy, Harvey? I'm just gonna leave that because I don't know.
You said equilibrium is death, and then started talking about reversing
Oh,
it.
nice. Oh, okay, I see what you did there. Okay. All right. Any other questions, or I'm gonna stop here. Get some food before I do the interview.
I mean, I have a question.
I'm cutting you off, Dallas. So I'm gonna take it off the recording. No, go ahead. No, go ahead.
All right. So the part that keeps getting me is reading straight from Wikipedia here. The second law of thermodynamics states that the total entropy of an isolated system can never decrease over time. And
Okay.
And it seems like in these couple previous examples, we're saying that a system that goes on its own has entropy that decreases over time.
No, we're saying once it's done its thing. Well, oh man, Dallas, we will take this one offline because I think that you're taking a very myopic approach to this, and you're almost pulling a Miss Young. I read something somewhere, and you're trying to put this square peg into a round hole because of one thing you're reading. You really have to look at it in the overall aspect. As we get further along into our careers here, we really have to realize that we learn one thing, but that one thing doesn't apply to everything. And we are rapidly getting out of that one thing controls the rest. And so it is a combination of different things. The entropy of an isolated system, this wasn't an isolated system. We took cobalt and we dumped it into water. That's not isolating it. It's letting it do something. So again, I'm giving you guys, and I love this part of your education, and it only gets worse. I'm giving you guys enough information to be dangerous if it's not applied correctly. And so you got to be cautious in taking whatever new thing you get and applying it to everything, which is a natural thing to want to do. I still do it myself when someone gives me a new piece of information, and I always have to check myself. So I'd encourage you to check it before you wreck it and realize it might be just a piece of a much larger puzzle. With that, I'm going to go ahead and stop it, and then you and I can chat a little bit more if you want.
All right.
I don't want to